Hey guys, this is Carrie, and this is lesson 3 in Unit 11. So, starting off, draw the two reference triangles below. Hopefully you pause now, give the do now a shot on your own, and then come back to it if you find yourself wanting to review it. Okay, so now that it's time to review the do now, let's draw the two reference triangles below. The 30, 60, 90 triangle, these are going to be your angles. So we draw a triangle with a 30-degree angle, a 60-degree angle, and a 90-degree angle. And now the sides are 1, 2, square root of 3. Instead of 1, 2, 3, 1, 2, square root of 3. All right, next up we've got our 45, 45, 90 triangle, and again, these are the angles. So I'm trying to draw this one so that it looks like these two angles are congruent, because they're both 45 degrees, and this one is 90. And then 1 and 1, because since these angles are congruent, the opposite sides will be congruent. It's an isosceles triangle. And then this one here will be square root of 2. So, in memorizing these two triangles, perhaps it's useful to see some patterns here. Both of them have a 1 here and here, as long as you're conscientious about always putting the 30 and 45 degree angle here. Both of them have something like a 2 here. Here it's 2, and here it's square root of 2. And both of them have a single thing that has a square root. So if you can remember that, maybe that makes it easier to memorize these. But they're really useful to have memorized, because once you have them memorized, you immediately know all of these problems for problem 2. The sine of 30 degrees, well, that's going to be opposite divided by hypotenuse, as always. So that'll be 1 over 2. And in case this isn't fresh in your memory, you can always remember sine, cosine, and tangent by using the mnemonic TOA, which shows the fraction opposite over hypotenuse, adjacent over hypotenuse for each of these. So tangent of 30 is going to be opposite over adjacent, so 1 over square root of 3, and we're done. And cosine of 45 degrees is going to be, picking either 45 degree angle, I like to pick this one, cosine is going to be adjacent over hypotenuse, so 1 over root 2. Okay, so now no calculator allowed on this one. We recognize right away it's 60 degrees, so we're feeling really good about this angle because it's one of our familiar angles. Let's take a look at how we solve this problem. So before you use the calculator, or before you use the reference triangles or anything, we're going to try to set up an equation. So we've got our focus angle, which lets us label our opposite, our hypotenuse, and our adjacent. And so we find that the sine, well, hold on. Let's write our acronym out, or our mnemonic out. So, TOA. Now we're trying to avoid hypotenuse because we don't know anything about that, but we have information about the opposite and adjacent. So we're going to cross out all the ones that have an H for hypotenuse, and we're left with opposite over adjacent. That looks good. So here we go. Tangent of 60 degrees is equal to opposite over adjacent. Now, how would you do this without your calculator? Well, good news is we know the tangent of 60 degrees from our reference triangle, because that's one of our nice angles. So we go 30, 60, 90 triangle, and then we have the triangle. If you didn't have it above, you would redraw it. You don't have to redraw it because you probably have it on the same page, but I don't. So here we go, 30, 60, 90, 1, 2, square root of 3. And for tangent is opposite over adjacent. And this time, we're focused on our 60 degree angle. So opposite over adjacent will be square root of 3 over 1. And that equals our 16 over x from before. Now we multiply by x on both sides. Square root of 3 over 1, well, division by 1 doesn't matter, so that cancels out in some sense, or dividing by 1 doesn't change anything, so we get x times the square root of 3 equals 16. And the last step to solve for x here is we had x times this, so we divide by square root of 3 on both sides, and that gives us x equals 16 over root 3. Alright, so if you had any questions up till this point, you should pause, rewind the video, and see if you can answer your questions. because we're going on to a lightning round. So one important thing to know about this lightning round, other than that it won't be two flashy lights, I don't actually know how to do that. Let's see, maybe I can do that like this. Ooh, lightning round! Oh cool, I'm excited, that worked pretty good. Is that for some reason, instead of putting degree signs, my computer put this symbol. So this symbol always just means degree sign in the presentation. I'm sorry about that. So here we go. Determine the value of the given quantity or solve for the variable. No calculator allowed. Alright, so lightning round time. Alright, so here we go. Determine the value of the following trig function without a calculator. So you're probably going to be using your reference triangles. And that should say sine 60 degrees, but this thing, I don't know why it's there. It should be a degree sign. Sorry. Tangent 45 degrees. It should be a degree sign. Sorry. Cosine 30 degrees. All right, next up, find the value of theta. So here we go. Oh man, sine of theta is 1/2. I wonder what angle would do that. Maybe the reference triangles are useful. What angle makes sine theta 1/2? Tangent of theta is 1/√3. Which of the two triangles are those numbers on? Which angle would give us opposite over adjacent for this? At number 6. Okay, so let's go back to the lightning round here. So I don't have the problem, so I'm just going to have to do a quick little back and forth here just to memorize them. Alright, so it was sine 60. So sine 60 degrees, we go to our reference triangle, and that's going to be opposite over hypotenuse, √3/2. Next up, I think, was cosine. Oh man, cosine or tangent of 45. So tangent of 45, we go to our other triangle, opposite over adjacent, 1/1. So tangent of 45 degrees is 1/1, which is just 1. Next up, we had, sorry about this is not ideal, cosine of 30 degrees. So we go to this one here, cosine of 30 is adjacent over hypotenuse, so √3/2. For the next one, we had sine of theta is equal to 1/2, and we needed to know what theta was. So if we look for our two reference triangles, we're wondering which one has side lengths of 1 and 2, and which one has that for the opposite and for the hypotenuse. So it looks like for the 45, 45, 90, the hypotenuse is square root of 2, but we want the hypotenuse to be 2. So we know it's not this one, which means we're on this triangle. And is there an angle here that has sine equal to 1/2? Well, yeah, that's 30, because opposite from 30 is 1, and then the hypotenuse is 2. So theta must be 30 degrees. For problem 5, we had, let's take a look at it. We had tangent of theta equals 1/√3. So we're looking for 1 and √3 as the opposite over adjacent, because in SOHCAHTOA, tangent is always opposite over adjacent. So 1/√3, that's going to be 30 degrees again, opposite over adjacent, 1/√3. So theta here is also 30 degrees. And then finally here we had cosine of theta equals 1/√2. And because this is in SOHCAHTOA adjacent over hypotenuse, we know that this one has to be the hypotenuse for √2. So we know we're on the 45, 45, 90 triangle. So we know that theta is 45 degrees. Okay, so here we go. Continuing on. All right, so answer each of the following questions. Use your calculator to find the value of sine 210 degrees. What are some strange things about this question / this answer? So go to Desmos, make sure you're in degree mode, punch that in, see what you get. Okay, I'm going to do that too. So here we go, sine 210 degrees. So making sure we're in degree mode, yeah, degrees are selected. Functions, sine 210 degrees. We get negative 0.5. So there are some things that should be pretty alarming about this answer. So if you haven't found anything alarming yet, pause for a second and think, what's weird about this? Well, there's a couple things that stand out to me. First off, 210 degrees? What? These are supposed to be angles in a right triangle. And so if you have a 90-degree angle here, how are you even going to have a 210-degree angle here? What does that even mean? And if we have a 210-degree angle, that's like bigger than obtuse. So how do we even fit this angle in a triangle? This is all pretty crazy. But the craziness, let me just expand on what I was saying. 210 degrees is too large of an angle. And then also something really weird is, how is it that we're getting a negative number on the right-hand side? Why is this negative? And it really makes no sense to get a negative number here because sine is supposed to be equal to opposite over hypotenuse. So we've got opposite, we've got hypotenuse. So how is it possible that we're taking the ratio of a side, which has to be a positive number because it's a length of that side, and another positive number, and somehow we're getting positive over positive equals negative? So there's some weird stuff going on in our calculators, and what that usually means is there's some more math to discover. So we're going to try now to break free of the right triangle interpretation of trigonometry. So now we can fit angles that are bigger than, 180 degrees or bigger than 90 degrees into our definition of what it means to find sine, cosine, and tangent. And in order to do that, we have to scrap this idea of a triangle and start to think about the coordinate plane. So we're going to start off by graphing a couple of angles in the coordinate plane. And then what we're going to do is we're going to see how these ideas in the coordinate plane connect to our ideas with SOHCAHTOA and allow us to redefine sine, cosine, and tangent in a really useful way so that we understand exactly why this is true. In fact, we'll be able to do that without the calculator by the end of this unit. So here we go. Draw the specified angle in standard position. Specify the quadrant where the terminal side of the angle lies. All right, so some vocabulary. For standard position, your angle is going to be always starting on the x-axis. And your angle is going to always open upwards clockwise or counterclockwise. Oops, sorry. It's hard to say these words. So it starts on the x-axis, so this is the starting side. And then it opens counterclockwise, so backwards from how a clock would go. And since this one is 47 degrees, it's going to open 47 degrees counterclockwise. And then the side where it ends, where the opening of the angle ends, is called the terminal side. And it's very useful for us to keep track of which quadrant the terminal side ends in. So remember your quadrants are labeled 1, and then counterclockwise 2, 3, and then 4, using the Roman numerals. So in this case, our terminal side is in quadrant 1. And we're only keeping track of the terminal side because our starting side is always going to be in the same place. So for 160 degrees, let's do the same problem. Well, here we start with our starting side on the x-axis. And we want this to open a total of 160 degrees. And so if we start off here, we know this isn't 160 degrees yet because this is still an acute angle. This is how many degrees if we were to open straight up? And that would be 90 degrees, right? And we don't want 90 degrees. We want a little bit past 90 degrees. So we're going to erase those. If we went all the way horizontal, that would be a complete 180 degree angle. And we don't want 180 degrees, so we're going to erase that one. What we want is we want 160 degrees. So that will be somewhere just before 180 degrees. And this looks like what we might expect 160 degrees to look like, because it's an obtuse angle, bigger than 90 degrees, but smaller than the 180 degrees straight angle. All right, so which quadrant does this end in? Well, we label our quadrants 1, 2, 3, 4. And our terminal side The ending side, terminal means ending, is in quadrant 2. All right, for problem number 3, this one is the craziest one, 275 degrees. We start in the exact same place. If we open to here, that's a right angle, 90 degrees. That's not what we want. If we keep going another 90, that will be 180. That's not what we want. If we keep going another 90, let's see, 180 plus 90, that's 270. So we're getting closer to what we want, but we want 275, so this is going to be 5 degrees past 270 degrees. And so we end up with this giant Pac-Man style angle. But we've got it right because we were careful with our axes and making sure that it landed in the right spot. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So it looks like we're ending in quadrant 4 this time because our angle is bigger than 270. All right, so next up, you guys are going to get some practice drawing angles. So please take a look at the next page and see if you can figure them out. All right, so drawing each of the specified angles in standard position, in what quadrant does the terminal side of the angle lie? 95 degrees. Well, I always like to label these with, well, the 0 would be if we didn't open the angle at all, right? This would be 90, this would be 180 degrees, this would be 270 degrees. So we know for this one we're a little past 90. Here's 95 degrees, which is in quadrant, let me change colors here just so it's visible, quadrant 1, 2, 3, and 4. This is in quadrant 2. 184 degrees is going to be a little bit past 180. So we have 90 straight up, because that's a right angle. We have 180 here. So this will be 4 degrees past that, 184 degrees. And so that ends in quadrant 1, 2, 3, 4. Quadrant 3. 350 is just short of a full circle, 10 degrees short of a full circle, so that's quadrant 4. And now you guys got problem D, so I'm going to leave that. 370 degrees, something strange happens. We actually go beyond a full circle, and this is okay. Before it wasn't okay. Now that we're looking at the coordinate plane, let's see how it works. So our starting side is here. If we don't go anywhere, then that would be 0 degrees open. If we go here, that would be 90 degrees. Here, that would be 180 degrees. Here, that would be 270 degrees because that's another 90. And then if we go full circle, that would be 360 degrees. So this is going to be 10 degrees past a full circle. So if we draw the whole angle all at once, it's like this weird little spirally angle that opens past a full circle. So this is our 370 degree angle, and it lands in quadrant 1. For this one, 500 degrees, let's see, 500 degrees. Well, that's going to be past 90, past 180, past 270, past 360. If we go 90 more degrees, that would put us straight up here. That would be 450 degrees. So it's past 450 degrees. And it's 50 degrees past that to reach 500, so 50 degrees past that would be here. And so a 500 degree angle is a big spirally angle that lands in the second quadrant. All right, for these negative angles, we're only going to go over one of them. Let's just pick angle, or number H, letter H. What do you think negative means when it comes to angles? And there's so many ways to interpret this. So if you didn't interpret it the correct way, don't stress it. I mean, it's just kind of like how mathematicians have decided that a negative means this. What the negative means is instead of going counterclockwise, you open the angle in the opposite direction. Open the angle in the opposite direction. So what that looks like here is, even though it's negative, the starting side is always on the x-axis. But because it's negative, instead of going this way, which is the positive way, we actually go the negative way, which is downwards. So going the negative way, this would be negative 90 degrees because we've opened it 90 degrees in the wrong direction. This would be negative 180 degrees because we've opened it 90 degrees further in the wrong direction. And this would be negative 20 more degrees, which would put us at a total of negative 200 degrees. And so we end up in, the quadrants are still labeled the same way. They don't reverse. These are labels that are existent outside of what we've done with the angle, but we still end up in quadrant 2. So negative just means you open the angle in the opposite direction, which is clockwise, as opposed to counterclockwise. All right, continuing on. So the goal is now we know where these angles are going to be, right? We graphed all these big angles in the coordinate plane. How do we connect with this with our idea of SOHCAHTOA to define right angle or trigonometry for these? So let's start by looking at only angles whose terminal sides lie in the first quadrant. It turns out that these are the easiest to work with because both numbers are positive and because our angle is of a reasonable size. And when we do this, I think we're going to find a pattern. So we're going to see if we can build up some insight for angles that extend to other quadrants. Sorry about the typo. The terminal side of an angle passes through the point 8,6. The length of the line segment from the origin to the point 8,6 is given as 10. Okay, so if we look at our picture, we see that this length is 10. And then we think about 8 and 6. And the way that this problem is presented, it's not obvious where these numbers are coming from. But if we think about it, 8 is the x-coordinate, so we must have gone 1, 2, 3, 4, 5, 6, 7, 8 units this way, and then 6 units in the y direction in order to get to that point. So if we think about this graphically, it looks like we went 8 units to the right and 6 units up. And thinking about that graphically with those x and y coordinates makes something really apparent. There's actually a hidden right triangle in this picture that we didn't even see before. We just had our angle and our distance. So because there's a hidden right triangle here, we can actually find the sine of theta, the cosine of theta, and the tangent of theta using SOHCAHTOA. So sine is opposite over hypotenuse. So if we use theta as our focused angle, we go opposite over hypotenuse, and we get 6 over 10. And I know that can be reduced, but in this case, I think 6 over 10 is the best answer because it's evident where it came from in our problem. Cosine of theta is adjacent over hypotenuse, so we're going to use the adjacent side over hypotenuse, which is 10. Tangent of theta is opposite over adjacent, so we'll use 6 over 8. And I'm not reducing any of these intentionally because I like showing where they came from. It's nice here. All right. So next up, you can use this idea pretty frequently. So I'm going to ask a couple of challenging extension questions to this one. So without finding theta, write the sine of theta, cosine of theta, and tangent of theta as fully simplified fractions. So immediately I write sine is opposite, so, SOHCAHTOA. Okay, and we need a triangle. So if we draw our triangle here, we go 12 units in the x direction, and then 5 units in the y direction to graph this. And that creates our right triangle. But what makes this one a little more challenging is they didn't actually tell us the distance here. They didn't tell us the hypotenuse. So I'm going to put an x there. And if we wanted to find x, well, because we know two sides of the triangle, we can use the Pythagorean theorem to find x. So we do a squared plus b squared equals c squared. A is going to be 12, b is going to be the other side, 5, and c is always the hypotenuse, so we plug in x there. 12 squared is 144, plus 5 squared is 25. 144 plus 25 is 169. And if you take the square root of both sides, you find that x equals 13. Now that we've got our three sides, we'll be able to use these in any combination, opposite, hypotenuse, adjacent, hypotenuse, whatever we want. So sine theta is our focus angle, opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent is theta. Pause for a second, see if you can write it down. It's 5 over, because this is the opposite, over the adjacent, which is 12. All right, so these are all really powerful ideas, and we're starting to get a feel for, even if we start with no triangle, just erasing all this work, you can rewind it to see it. Even if we start with a situation that has no triangle, the triangle is kind of implied. So here we go, one step more difficult. An angle theta is graphed in standard position. The terminal side passes through the point P is 7, 24. Which of the following trig ratios is correct? All right, with trig problems, if they don't give you a picture, it's always helpful to draw one. So we're going to draw it in standard position. So that means that our axis starts on the x-axis. Now, we know that the terminal side, the ending side, goes through the point 7, 24. So 7 and 24. I'm not going to draw all the tick marks because that would take a really long time. But we know it goes a little bit in the x direction, 7 in the x direction, and then 24 in the y direction. And so because we go 7 and 24, mentally we're starting to see that triangle as we plot. And because the terminal side goes through this point, we need to draw our terminal side right here. And I drew the terminal side a little bit too long, so I'm going to erase that. And I'm going to make it so that the terminal side, whoa, too much erasing. I'm going to make it so that the terminal side goes to that point. Okay, so just like last time, oh, and we have to put theta in. Theta is how open this angle is here. So we're going to put theta here. That's the angle. All right, now that we've got everything drawn, we can find out what we need. So we need all three sides. We've got 7 and 24. We've got to find the hypotenuse. So I'm going to call that x. So we're going to do a squared plus b squared equals c squared. 7 squared plus 24 squared equals x squared. 49 plus 576 equals x squared. 49 plus 576 is 625 equals x squared. Take the square root of both sides. X is equal to 25. And if you're wondering how I did that so fast, I just have it memorized. This is a really common problem, or common set of numbers, and I didn't actually add those that fast. I just knew what it had to come out to, so I cheated a bit. But we know the hypotenuse is 25 now. All right, so let's see. We've got our opposite, we've got our adjacent, we've got our hypotenuse. Take a second to see if you can pick out which of these is correct. Well, we know tangent is supposed to be opposite over adjacent because of so, ka, toa. And this is not opposite over adjacent. Sine is supposed to be opposite over hypotenuse. Opposite is 24, not 7, so this is not correct. Cosine is supposed to be adjacent over hypotenuse. Adjacent, yeah, that's the one. But let's see about the last one. Sine of theta is supposed to be opposite over hypotenuse. That's the adjacent, so that doesn't work. Cool. So hopefully this makes a lot of sense. What we're doing here is we're building right triangles out of our angles in the coordinate plane. So take a look through the important stuff. Make sure you do all the problems. You're going to earn a couple of checkpoints here. So checkpoint 2, checkpoint 3, checkpoint 4. And I think checkpoint 4 is a pretty remarkable problem because we take away all of the numbers in the problem. This is the key problem in the whole lesson that's going to lead us to where we need to go in the next lesson. So spend some time with this one, even if it's a little difficult at first. It's very important. All right, and then there's some tough stuff, which is optional, of course. So I hope you guys found this lesson interesting and educational. The goal is, how do we find the sine, cosine, and tangent of angles bigger than 90 degrees outside of a triangle? And we started to build that up, right? We've got angles in the coordinate plane, and we're starting to connect SOHCAHTOA to these angles. It's not complete yet. That's going to be next lesson. But I'll save that for next week.